Okay, again, if we have a heatsink attached to the device like here, so we consider this one is a MOSFET, 3 outline terminals attached to the heatsink. Yeah. So the equivalent circuit will be, in terms of electrical equivalent circuit, will be source of current with 3 elements of thermal resistance. So in electrical, you can represent as here as V3, here is V2, here are V1, and here we can put as V0. So we do analysis using Ohm's law for this circuit using V equal to delta V equal to IR. So for the first R1, V3 minus V2 is equal to I times R3, or V3 is equal to I R3 plus V2. This is the first equation. Then for R2, the voltage difference is V2 minus V1 equal to I R2. We arrange again, we get V2 is equal to I R2 plus V1. This is labeled as option number 2. Then for R1, V1 minus V0 equal to I R1. We arrange again, V1 is equal to I R1 plus V0. This is number 3. So 3 you put into 2 becomes V2 is equal to I R2, here I R2 plus V1. V1 is I R1 plus V0. Okay, so this one become 4, equation 4. So 4, you put in equation number 1 here, it becomes V3 is equal to I R3 plus I R2 here, this one, plus I R1 plus V0. So you rearrange, we get V3 is equal to I R3 plus R2 plus R1 plus V0. So this is the same like this one. If we transfer all the value here from electrical to thermal equivalent parameters, V3 become TJ, I is the PD or the thermal RTH of JC, CS and SA, and this is your ambient V0. So this is how this equation is generated from the circuit. Okay, next we'll discuss regarding power directing curve. Okay, not all datasheet or most of datasheet, they don't present or they indicate their reduction or the directing curve inside their datasheet, but they prefer put in terms of table, the PD, yeah, PD of how much at certain ambient or at certain case temperature, and TC is temperature of the case at certain level, how much ability of the PD, dissipated power that the device can absorb or extend. Okay, the device power capability will reduce as the case temperature increase. Means that if your case temperature is normal at ambient, this is ambient at 25 degrees C, increase further to maximum, so the ability of your PD here will reduce accordingly, and it will reduce accordingly. It's normal at maximum. So the rate will depend on the device thermal resistance, and we'll see later, and also depend on the maximum junction temperature which is allowed for that certain device. So the slope will show the curve of the directing power in terms of watt per degree C. How many watt, how many degrees C is increased, so that's the amount of watt you have to reduce. So this is slope of watt per degree C. The higher the junction, the higher the case temperature, the lower the PD limits will reduce. So you have to take care. It means that the ability of the device will reduce accordingly when your case or your operating temperature increase. So for example, if we indicate in terms of table, or in terms of graph, sorry. So this is the ability of the device. Maybe it can absorb, or it can withstand up to 100 watts, provided your case temperature is at room temperature of 25 degrees C. But if you expect your device to operate at certain value of 45, 65 or 75 degrees C, so the ability or the maximum dissipating power of the device will reduce accordingly. Maybe at 75 degrees C, the capability is normal at 100, but it reduced, or we have to limit to 10 watts instead of 100 watts at 25 degrees C. So over here we have a certain table from the datasheet that we have picked up previously. This is total power dissipation at ambient temperature of 25 degrees C. You can dissipate up to 56.6 watt. If the temperature rise above that, means that normal at 25, maybe 26, 27. So for each of degrees C increment, you have to minus 0.38 watt. And directed above 25 degrees C will take effect on this kind of value, 0.38 watt per degree C. So you have to minus 56.6 minus 0.38 minus 0.38 and so on. Okay, for the other parts, indicate in terms of how much case temperature at certain case temperature. This is the amount of maximum or limits dissipating power that the device can hold or can withstand. So this the linear dilating factor. For each degree C, how much you have to reduce the capability now. 82 minus 0.5 minus 0.5, so on after, and up to your operating temperature that you expect the device to operate. So it's mentioned over here that the PD maximum, this maximum value here, can be applied if you are able to maintain the TC or T ambient at 25 degrees C. So this ideal scenario is for sure it's impossible to be practiced now. So you have to consider at certain value above that, how much you have to direct the PD maximum limit to. Okay, next, for example, as what we have discussed before, if the device, we have a device which attached to the heatsink with this kind of scenario, 80 degrees C limit, we limit our junction at 80 degrees C. So the PD dissipating power is 16 watt PD, and our ambient temperature is 40 degrees C. Thermal resistance from junction to case, TJC, is 1.25 degrees C per watt. Thermal resistance from case to heatsink, which is the washer, the parts that we use to attach heatsink and between heatsink and the device, we take as 0.5 degrees C per watt. So what we need to do is that we draw the equivalent thermal circuit, and we jot down all the information that been given to the circuit. How much PD, how much TJ, TC, TS, and so whatsoever. So we know which one or which part that we need to calculate based on the parameters or data that been provided. In general, this is the formula that we're going to use. We have learned how the formula being generated, so we just use for the analysis. So it's given here, TJ how much, PD, R thermal JC, R thermal CS, and ambient. We list down all the information that given, and we try to find out what are the parameters that we need to find out. So we need to find the heatsink thermal resistance. So when we put in all the data into the formula, we get that ambient temperature, oh no, this is the TC, RTS, sorry, RTS not RTA, is 0.75 degrees C. Okay, it is R thermal SA, which is the value of the heatsink. Based on what data that we have, we put into the formula. We are able to calculate or investigate and come up with the value of the heatsink that we required for that scenario. Okay, like just what we have discussed just now regarding the equivalent circuit when we put a device on the heatsink. We use just now the equivalent electrical circuit to calculate how actually the formula being generated. So you can use directly the thermal equivalent circuit and generate the same step to produce the formula throughout this circuit analysis as well. So you can give a try. So in general, once we are able to draw the equivalent circuit power diagram of our converters, we should be able to draw the equivalent thermal circuit which need to be used to analyze our thermal scenario or thermal heatsink consideration for that circuit. If we use individual heatsink, so this is how the circuit or equivalent circuit of the circuit should be drawn. This is for AC/DC, and we have four devices, so each has its own heatsink. So R thermal JC for device number 1, number 2, number 3, number 4, and this is the heatsink. So this one is for common heatsink, means that all the devices are sharing one heatsink. One heatsink placed with the four devices here. So all come to the same heatsink. This is what's so-called common heatsink. Meanwhile, this one is the individual heatsink. One device with one heatsink. So this is also common heatsink. Two devices, two thyristor for the AC converter placed on one heatsink. So this is a simple buck converter. We have two devices mounted onto one heatsink. So this is example of common heatsink that being practiced. Okay, later we'll discuss about regarding this DC converter, which use certain part number, consists of diode and MOSFET. So we'll proceed on the next slide for this example.